Можно начинать?
Ну, возьмите. А вы не будете?
Нет, я не буду комментировать.
Ну, я понимаю, что не так активно. Нет, ну нет, ну не хотите, не надо. Это не так, но нет, но передавать просто его в любом случае удобно. Так что я думаю, среди всех сидящих вы, скорее всего, будете что говорить. Ну, здесь мы куда просто доклад оставим. Так как угодно, вот так нормально.
Я потом еще окей, we start.
So in English, yeah.
In English, yeah.
Okay, so I want to thank Sergey Lando for opportunity to give a talk in the seminar. Unfortunately, I don't know very well how much this you will know, so information is access. Sorry, this is not really.
That's
Okay, so I will speak about different approaches to calculating not polynomials, not polynomial invariants. And the plan of my talk will be as follows. That I will start from some motivation of why I studied these different approaches, why is it interesting, both from a mathematical point of view and from physical point of view, because my background is in physics, not in mathematics. And then my talk will have two parts. So the first part are different approaches which are based on a classical approach suggested by Точные and derived, which is to calculate mathematics using matrices. But we heavily modified these approaches now, and there is some different modifications which are both more effective, give us more information, and explain some deeper structure. But they are based on the idea of Verstegen and derived from 1990. And the final part, I will talk about an approach of different type, which is not based on our matrices. Basically, the motivation for this approach is to study the different type of knots, virtual knots, which are knots in non-trivial space, topologically non-trivial space. But I will explain it in more details when we get there. So let me start from some motivation. Basically what we want to study is some polynomial, in mathematics these are polynomial invariants, and in physics these are Wilson loop averages of Черна-Саймонsa theory. So it is some three-dimensional theory which is topologically invariant and has an action of following type. And Wilson loop averages, they depend on this averages of a certain type, which depend on a contour in a three-dimensional space. And this theory is topological, so all its averages,
sorry, the
yeah.
was a space of flat connections.
Yeah, yeah.
I was always puzzled how well it is defined.
Yeah, it's an interesting question, and basically the approach which I tell you about is exactly the method of defining this integral, but the motivation comes from this part, and also from here, as far as I understand, comes the motivation of what we want to study here. Yeah, so basically we want to study these Wilson loop averages, and we know that they are topologically invariant, and they're basically equal to two quantities in knot theory. These are polynomial invariance and the Kontsevich integral. And the equivalence goes as follows, that we can show that these two are equal, and then we can show that these two are equal, and we can presume that these two are equal also, and provide a method of calculating these things from coming from here. So basically, these Wilson loop averages have a certain number of parameters. So first, they depend, of course, on the parameter of the theory K. This is also called level of Chern-Simons. Then there is some gauge group, let me call it G. And there is also what is there's, of course, this contour K, which is basically a knot because it's some contour in three-dimensional space, which should not self-intersect. And also, there is a very important parameter, the representation of this group G, which we'll enumerate by Young diagram Y. And basically, we want to study the dependence on same parameters here when we study polynomial invariance. And we know that this connection exists, and that basically for different values of these parameters, we will get different polynomial invariance. So let me start from group G, that for different groups, we get different types of this polynomial invariance. So for group SU2, for example, we get Jones polynomials. For group SUN, this will be Homfly polynomials. One moment. Yeah, for SON, this will be Kaufman. And for other groups, I don't think they have some specific names. Knot K, of course, just represents a knot for contour K, just represents a knot we study in this part. So this value K, as well this is this N, enter just these polynomials through their variables. So Jones will depend, for example, on Q, Homfly on Q and A. And we will basically speak about Homfly polynomials. Jones are their particular case, as we can see here. And almost all methods can be generalized also to Kaufman polynomials, but it's a little bit different story. And so Q, from the point of view of the physical part, is just an exponent of this level K, and A is equal to Q to the power of N. So you can see that if I put A equal to Q squared, I get just the Jones polynomials. And the interesting part is this representation Y, which is exactly related to this previous question, that we are very interested in this representation. And basically what this means on this side, that we should study a covered polynomials, covered with exactly this representation. And basically we are very interested exactly in high representations. Well, first of all, because simple fundamental defining representations are very simple and we know almost everything. And second, there is lots of connections of different theories with Chern-Simons theory and with knot theory, like integrable systems, matrix models, all of which give some interesting results when we study these covered polynomials. And also, these covered polynomials are very interesting from, so to say, the basic idea of knot theory. because so the basic idea, as I understand, was that we want to distinguish knots. Yeah, we want to understand if two knots are the same or different ones. And for this, this invariants were suggested because it's much easier to compare polynomials than to compare something in three-dimensional space. And basically what we want from this polynomial invariants, of course, we want them to be invariant, so we want them to coincide when knots coincide, but also would like for them to be different when knots are different. And this is where these representations come from, because if we study just the usual non-colored Hornfly polynomials, they coincide for lots of knots. But even if we study some colored representations, there is a certain type of knots called mutant knot, for example. This works as follows, that if I have some knot, I cannot draw mutant knot exactly, so I'll draw just something. And we can divide it in two parts. So we can cut off some tangle with forced sphere, and then just rotate this tangle by 180 degrees in some direction, either in this direction or this direction, in any direction. This operation is called mutation. And we know that for any symmetric representation, actually Hornfly polynomials, as well as Jones polynomials, and I think also Kaufman polynomials, they are the same for these two pictures. And for high number of representations, this operation does change the knot. So these are two different knots, but the polynomials, for fundamental polynomials and also polynomials in all symmetric representations, coincide in this case. So even from this basic idea of knot theory, we are very interested in studying these colored representations. And actually using these methods, we managed to calculate polynomials of some mutant knots which are different.
Whether one is able to say whether the representation is symmetric looking at its Young diagram.
Yeah, so what I'm calling symmetric is when the Young diagram, in a sense, it doesn't matter because, well, I call these Young diagrams of this type symmetric and this anti-symmetric, and both of them are actually kind of the same from the point of view of Hornfly polynomials, because there is a mirror symmetry which says that transposition of diagram corresponds to the inversion of Q. So we need some representations corresponding to Young diagrams which are not a row or a column, which are more complicated. So this is why we are interested in studying exactly the dependence of this representation. Okay, so now that I spoke about the motivation of these studies, let me start by defining what we are studying exactly. So we will speak about Hornfly polynomials, and basically when they were introduced, the non-colored Hornfly polynomials, they were introduced through the scaling relations, which take a knot, then take some crossing in this knot, and replace it in three different ways. Like this, or when representations do not exist. And a Hornfly polynomials of these three knots are related by a following relation.
So you mean you take plane diagram?
Yeah, of course. I project the knot on the plane and then speak about the diagram of a knot.
It's important remark, especially at our end, because
Yeah.
we usually do not consider diagrams, not diagrams.
You consider knots in three-dimensional space?
We consider knots in the three-dimensional space as well as chord diagrams. Associated to singular knots in a three-dimensional space.
We will mainly speak about knot diagrams. We'll almost only speak about knot diagrams. Yeah. So, and it should be equal to this one. And basically, if I take this relation and that to them that I know when two knot diagrams represent the same knot, which are, so if two knot diagrams represent the same knot, one can be made into another by 3 Reidemeister moves. So this is equal to this. This is equal to this. And a third one, which will be the most interesting to us in a sense, this one. That, oh, I get the same. Like this. Basically, using these relations, I can define this knot polynomial. By define, I mean that I can write a knot polynomial of any knot through the knot polynomial of just a knot, which can be put to 1 or can be put to something else. It depends on the task we're interested in. This is how the non-colored Homfle polynomial, the polynomial which corresponds to the fundamental, to the defining representation of the group, looks like.
So here, by not you mean also a link?
Yeah, not a link. Yeah, it almost doesn't matter at this moment. It matters in a sense when we speak about higher representations, that for a link we can have different components covered by different representation, and then the situation is a little bit more difficult, but basically the same approaches work there also. Then, as I said, we're interested in higher representations, and the question is what is a good way to define these polynomials in higher representations? Well, the first question is, can we modify this? This is called scaling relation. Can we modify it to give us answer for covered knot polynomials? The answer is, on one side, yes, we can. So, for example, if I want to study representation with Young diagram just 2, I can write kind of the same relation with some additional coefficients, but also I need to add one more term there, which corresponds to 2 crossings, like this. So I can write the same relation, it will hold, but the problem is that I'm not able to, using this relation, I'm not able to get from any knot to this knot, because it is too entangling, yeah, so to say. So I have a relation with 4 terms now, this, and this, with some coefficients. I can write them down, but they're not very easy.
This relation does not allow one to simplify.
At least I don't think so. I don't know the theorem. So here I know the theorem that it is possible to simplify. Yeah? Here I don't know the theorem and I cannot simplify it for all the knots. So we need some kind of different approach. The approach which was usually used, as I understand, in mathematics was that, well, we can look at this theory of these representations and see that basically if I take some power of defining representation, that in this power defining that all representations are present in some power of defining representation. So for example, this representation is present in just the square of defining representation. And from this comes the idea of cabling, that if I want an answer in this representation, I should take my initial knot, but just replace a strand with a pair of strands. And this will be the answer in this representation. And from here, I can somehow project it on this representation and get the answer. But this is, of course, not a very easy problem because
Is there a Russian word for cabling?
I call it kablирование. I'm not sure what is the correct word for this. Because just I'm replacing a strand with a cable, yeah, with several parallel strands. Another kind of modification of this approach is to study the so-called satellite knots. This is when I take a knot, then blow it up into a cylinder, and then put some other knot on the surface of this cylinder. But basically, this is kind of the same because this is one of the satellite knots. Ну, слово кабель по-русски тоже есть.
Кабель есть, нет, и есть хотя кабельный узел это другое вообще.
Ну да. Ну, мы называли это каблирование. Okay, but what we studied is a different approach, exactly which is based on this idea by Verstegen and Duraev. So basically the idea is the following, that if we look at the knot diagram either from the point of view of knots or from the point of view of these Wilson loop averages, what matters are the crossings. Everything else doesn't matter. So the question is, what kind of operator should I put in these crossings for the answer to be topologically invariant? And the answer is this: that this equation, this Söderle-Meister move, look a lot like Young-Baxter equation, and the solutions to Young-Baxter equation are matrices. So basically, the idea is that I should put in each crossing some R matrix, and then I will get some topologically invariant answer for each knot. And for a particular choice of R matrix, I will get exactly my knot polynomials. And according to Verstegen and Duraev, the R matrix I should study are R matrices of quantum groups. So I have some operator with four signs, yeah, with four letters, which should correspond to my R matrix, which has two outgoing legs and two incoming legs. And the formula which represents the R matrix of quantum groups.
G is not the same as K. Yeah?
No, not the same. So they are the same when this Q is equal to 1. Then this is just a permutation operator, but then the answers are not very interesting. Yeah, so these R matrices are defined for quantum groups. Basically, the formula looks kind of the following. So what is quantum groups? Quantum groups has a somehow misguided name because quantum groups is actually not a group, but actually
Let's say Hopf algebra.
Yeah, Hopf algebra, yeah. Quantization of universal enveloping algebra or Hopf algebra. And basically it depends on this parameter of deformation Q, which exists everywhere. So this quantum group has the same number of generators as universal enveloping algebra or Hopf algebra. And basically for any quantum group, I can define such matrix, where here I have a sum over all simple roots, and here I have a sum over a product over all positive roots. So this is just a permutation.
Aij to the power -1. This doesn't mean that this is some number Aij.
This is Cartan matrix.
Sorry?
This is Cartan matrix.
But it is inverse.
Yeah.
Inverse.
Yeah. And this is just a permutation operator which permutes two spaces. The matrix can be defined in different ways depending on if I insert this permutation operator or not. Depending on it, it will have some a little bit different properties, but I will speak about a matrix of this type. So basically, using this formula, I can actually calculate this matrix for any group and any representation. So it acts on a pair of representations, and I can calculate it basically always.
This is an operator in the tensor square of some
representation.
representation.
In a product of two representations. So I can act with it on a product of two different representations. If I want to speak about links, they can be different. If I speak about knots, they're always the same. But for this formula, it doesn't matter. Just I have two representations, of course, of the same group, and I act on them with this matrix. And I can calculate it for any representation. The question is only how difficult it is. But actually, this is not the whole story, because besides this third randomizer move, which I satisfied by putting a matrix, I have also two more randomizer moves. So this one is easy. This one means that if I define this as an R matrix, then this one corresponds to inverse R matrix. Yeah, so their product is equal just to 1, to identity. The more difficult part is the first randomizer move, which says that if I take a trace over one of the spaces for this matrix, I should get an identity operator. And basically, if I put this matrix and try to calculate it, I will see that it is actually non-trivial. That this thing is non-trivial, and in no way it is equal to just identity operator. And the solution to this problem is that besides a matrix, I also have some matrices which correspond to the reversing of the line. So I choose some direction for my knot diagram, and then I have a matrices in the crossing, and I have reversing of the line at the top and at the bottom, which corresponds to some operator like this. So this is just a sum over all positive roots of H alpha. This also comes from the theory of quantum groups, and basically these matrices will later give us a quantum trace. And these are basically all the components I need to calculate knot invariance. So I just take some knot, for example, this knot. I put indices on all the lines, and I put their R matrices in all the crossings, and in all the reverse points, I put this matrices M. And then I collapse all indices. So this will be inverse.
It's inverse, not as a trace.
This is inverse, and this is the same. Because this is equal to this. But this is non-trivial. So basically, this approach gives us a possibility of calculating the answers for any.
So you need two representations because
there are two lines intersecting. Yeah. So I.
Two lines, but they can belong to different nodes.
To different components of a link. Yeah. This is just, I can put there the same representation, but this also works when they are different. So this approach is kind of universal. But there's certain problems with this approach. First of all, well, these matrices are actually quite large. So for example, if I study SU2 and just define a representation, they're very simple. So our matrix is just a matrix of a size 2 by 2, which looks like this. And M, sorry, 4 by 4. And M is a matrix of a size 2 by 2. But if I go to larger groups, then they will become bigger. They will become n for SUN, they will become n squared times n squared. And if I go to higher representations, it will be even harder and even bigger matrices. And also, what I want is I want to study Humphrey polynomials, where the dependence on n comes through the letter a. And so basically, to calculate a Humphrey polynomial using this approach, I need to calculate answer for SU2, SU3, SU4, and then try to find a general answer in this form, which is also not an easy task. So this is the reason why we want to somehow modify it, modify this classical approach, and present it in a different way. For this, we can use a property of a matrix of quantum groups, which is the following one. So a matrix, since we study Hopf algebra, there is a coproduct in this Hopf algebra, and there is an important property of our matrix that it commutes with this coproduct. In this way. What this means for our story, that if we take this product of two representations and act on them, and then look at some irreducible representation in this product. So y1 cross y2 is equal to sum over irreducible representations q. Then on each of these irreducible representations, our matrix acts in the same, on each of the vectors in this irreducible representation, in the same irreducible representation, our matrix acts in the same way, because it commutes with the operators which move us through representation. So I can rewrite this matrix in the following way, that I can write a matrix which acts only on the representation Q, and even more than that, it acts only on the highest weight.
So what do you mean the same way? You mean that each Q is invariant on the R? Or does it mean in the same way?
Yeah, that all the vectors in Q change in the same way. So I move through the Q, I move using these generators of the algebra. And these generators, when acting on the product of two representations, they commute with our matrix. So it means if I take one vector from Q and another vector from Q, they will change in the same way when I act with the matrix on them. So I can write this action in the following way. That matrix acts only on the highest weight vectors of representation Q, and then I just multiply this action by representation Q itself.
It acts on the space of multiplicities.
Yeah, exactly. On the space of multiplicities, or in other words, on the space of, we can write it as action the space of highest weight vectors. Which is useful if you want to calculate exactly how to act. And basically, this means that.
So the idea is to start with the standard representation and then consider its tensor powers and try to.
Yeah, basically, yeah. But actually not on that, you can consider not on the tensor power, but a product of different representations in the same way. So all these approaches, they're basically all works exactly in the same way for links, not only for nodes but also for links. So if I speak about this matrix, at least for simple representations, then this matrix becomes actually very simple, because it just reduces to its eigenvalues, which correspond to the representations Q. And these eigenvalues are actually very simple.
Q's are irreducible.
Yeah, Q's are reducible representations in this product. And so the eigenvalues correspond to these Q's, and they're equal to the following formula. So here, epsilon is a sign, which can be found just by putting Q to 1, and it is actually a sign which comes from action of permutation operator. Kappa is a second Casimir operator, and it can be easily written just through the Young diagram Q. So it's 1/2 of just sum over all boxes in this Young diagram, like this. So I and J enumerates boxes in the Young diagram, and just sum over all boxes, the simple formula. And this term has some history that basically, if I look at this third randomized move, well, in one of the forms, it doesn't tell me anything about normalization of a matrix. So I can normalize this matrix in any way I would like. But if I speak about not, so if representations are the same, if y1 is equal to y2, then I have this one, this move, which says me how I should normalize this matrix. And so this is exactly, oh, sorry, this is Q. And this is exactly,
That was my next.
This is exactly how it should be normalized for this to hold, for the answer to be topologically invariant. And this is called.
But it seems that you arbitrarily use notation Q and Y for the same.
No, these are different. So this is Q, which is this one, and this is Y, which is this one. So okay, if I speak about not, so if y1 is equal to y2, then I have this relation which says something about a normalization of this matrix. And the normalizations you will get if you expand this first randomized move is the following one. And if I speak about links, if they are different, then I cannot get this term because I don't have this relation. And actually, there's a property that says that a number of crossings, an algebraic number of crossings between different components is a topological invariant. So this means that the answer would be topologically invariant independently on how I normalize this matrix. So for links, I can put anything here. And the simplest, okay. The simplest way I can use these matrices is to put them in a braid. So I represent not as a braid. This means that I.
So what do you mean by normalize? How do you put the formula for lambda q, but you have not explained how do you use it? Where to put this lambda?
These are eigenvalues of our matrix. This is what I will write now. So the braid, the presentation of a knot through a braid is the following one, that I put some braid and then I close it like this. And I can have any number of strands in this braid, but let us first speak about the two-strand braid, because it is the simplest way we can demonstrate how to use this formula. Looking at this approach, what corresponds to this braid? So I should put a matrix in each of the crossing, and for a two-strand braid, there is only one parameter, a number of these crossings. So I should put r to the power of n, and then I should multiply it, in this case, by m to the power of 4. Yeah. But actually, looking at this formula, I can rewrite it in a different way. I can, so if I have representations y1 and y2, I can write the whole braid, the answer for the whole braid as a sum over the same representations q.
Do you always consider pure braid or not necessarily?
Pure braids? I'm sorry, I'm not familiar with the term.
Значит, коса, крашеная коса. Если каждая ниточка возвращается на свое место.
Da, yeah, pure braid in this sense. Well, if it comes to the other place, I should just put some additional crossings here. So I have a sum over this representations q of our matrix, this representation q to the power of n, and then this closure corresponds to a trace over all representations which I have here, but combining them with these matrices, I get actually a quantum trace, which gives me a quantum dimension of the representation. And this is the answer for Humphrey polynomial in this representation. And basically, if n is odd, then they should always be equal, of course, because this is not, and then representations are equal. Basically, for most of the, well, for two-strand knots for any representation, I can just replace this r here with lambda, just with the eigenvalue which acts on this representation. So the answer will be just this lambda q to the power of n times sq. And sq is a quantum dimension. Sum over q, yeah, this is the same formula. So S is a quantum dimension, which is actually related to the Schur polynomials. So Schur polynomials is how it is, they usually defined. Right. Better like this. How they're usually defined, they depend on the Young diagram and on some set of so it's a basis in the space of symmetric polynomials. So it depends on some set of variables x, but then we can rewrite it as a function of power sums. Where power sum is a sum of over all x's to the power of I. And this is usually how they are defined. But actually, if we study quantum groups, we need some specialization of these Schur polynomials, and we need to put p equal to pi equal to the following thing. What is interesting about this formula is that basically, if I look at what comes into this formula, so this lambda basically depends only on q. Well, there is this normalization coefficient, but it's easy to get out of the formula. So they basically depend only on q. So they do not depend on the group. So this lambda, they are the same for any group SUN. And this S depends on the group through A, but it doesn't depend on the knot. So they depend on the width of the braid. And so basically, we rewritten this complete polynomial in two distinct parts, one which depends on the knot, and another which depends on the group. And these sure polynomials are very easy to construct, and thus we can immediately get the answer for any group SUN just by knowing these eigenvalues. So we immediately get...
The sure polynomials corresponding to the Young diagram here.
Yeah, yeah. I can present some answers for them if it is needed. Yeah, and also for these sure polynomials in this special point, there exists another special formula which allows us to write them just by looking at the Young diagram. Like this. So I take Young diagram, I take boxes in this Young diagram, and then so here I just have I minus j, and here this is a length of the hook which connects the box ij to end of the column and end of the line. So in this case, ij is equal to 4. For example. So it's very easy to find this sure polynomials in topological locus, it's called. So basically, this approach allows us to calculate the answers directly for any group SUN without any hassle. So just immediately.
Понятно, почему такие должны быть небольшие шуры?
Нет, я только пытаюсь
Mm,
просто как мантру воспринимающую, там когда-то от нас Миронов, когда-то нам это все рассказывал еще лет 5-10 назад.
ну, вот кто-то эту формулу получил, я, честно говоря, не знаю, как ее получить. Тоже.
Нет, ну просто мы за эти 5 или 10, тут были 10 лет, чего-то поняли.
Да, да. Но это получается действительно специализация тех же самых функций, которые у нас для чисел губец. Вот такая специализация странная. По идее должно быть. А это только для этих вторических узлов?
Не, сейчас скажу. Yeah. Yeah, this two-strand, they of course torus ones, but we can also say something about other knots. So the interesting part,
It works for any braid.
yeah, but a little bit different. So basically, the interesting part comes when I look at three-strand braid. And here I have operate. Oh, yeah, sorry. So basically here I also want operators which acts not on a pair of strands, but on the whole braid. So I have matrix R1, which corresponds to data matrix acting on the first pair, and just identity operator acting on the third one. And matrix R2, which corresponds in the other way around. And basically, I can continue this picture to any number of strands I want. So I'll get some elements of braid group corresponding to these matrices. And in this way, this third Remeister move looks in a familiar way, that it is just R1, R2, R1 equal to R2, R1, R2. It is probably more familiar this way. This is Young-Baxter equation, or third de Meister move. So in a sense, I can do it in the same way, that I now look at reducible representations in the whole braid. And so now I sum over reducible representations in the cube of initial representation. And the trace again will be given by the same S's. The question is, what will I get? What will be the coefficients for this characters? And the answer is not very simple. So basically, I know how the diagonal R matrix looks like because I know its eigenvalues. But it is not always when I can diagonalize both this R matrix and this one. Sometimes I can, but sometimes I can't. Basically, I can do this when this representation Q shows only one time in the tensor cube of initial representation. Yeah, so for example, if I take the final representation, then I will get this one plus 2 times this one plus this one. So here and here, a matrix, the space of highest weight vectors is just 1 by 1. And so these matrices are just the eigenvalues. But here situation is a little bit more complicated because I can diagonalize, for example, R1, but I cannot diagonalize the R2 at the same time. And to define this, I need to, one of the ways to find the matrix is to study how the bases change. So what is the basis where R1 is diagonal, and what is the basis where R2 is diagonal? And basically, by definition of these matrices, so I have a product of 3 representations, and I can multiply them in different way. I can multiply first these 2 and expand them in the sum of a reducible representation. Let me choose some different letter, T. Then multiply by the third one and get this representation Q. Or I can do it the other way around. So multiply first the second and the third one and get some representation T prime and then get representation Q. So this is the basis where R1 is diagonal, because R1 acts on the product of these 2 representations and acts just with identity here. And this is the basis where R2 is diagonal. And in general, these 2 bases are related by a 6G symbol or a K matrix. So if I put here some general representations, then this will be matrix U, which is equal to a 6G symbol So its matrix elements are enumerated by these representations here, and the matrix element correspond to the following 6G symbol. And this gives us the following formula that R2 is equal just to this. And so the question of how to calculate the polynomial, and so the B is equal to the product of R1s and R2s corresponding to exact form of the braid. And so the question of how to construct the polynomial comes to the question of how can I find these Racah matrices. So if I can find all the Racah matrices, I know all the polynomials. And of course, if I put more strands here, I will get more Racah matrices, more different Racah matrices, because then I have R1, R2, I have R3, which is related by one more Racah matrix to this, for example, this basis, and so on and so forth. So the structure is general, just I get some additional Racah matrices for each additional strand. So how to calculate these Racah matrices? One of the ways is, of course, that I can just calculate them directly. So just using relations of a quantum group, I can just calculate highest weight vectors of these representations Q coming from this way or from this way. And this we have done for lots of representations, but it's not a very interesting story. So we'll speak about a different approach. Let us look at this Young-Baxter equation and substitute there our known formula for R2.
Here, there R1?
R1, oh, yeah. So this formula becomes the following one. And I can look at this equation and say that, let me look at this equation like an equation on U. So I know how R1 looks like. The question is, what is U? And basically, I can choose R1 to be diagonal. And even more than that, if I multiply R1 by anything, it doesn't change the equation. So if I change the normalization of R1, the equation doesn't change. So from here comes the so-called eigenvalue conjecture. We say that U is defined by a set of normalized eigenvalues of R. So basically, if I have some two separate cases where I have where the R matrix have the same set of normalized eigenvalues, the corresponding Racah matrix should be the same. This is this eigenvalue conjecture. And this is a conjecture because it is not proven in general. It is proven for SU2. It is proven for matrices of size 2 by 2. But in general, we have no counterexamples, but it is still a conjecture. And even more than that, we have for small matrices up to size 6 by 6, there is a general answer that if I know R1, I know what this matrix U look like. So for example, for the size 2 by 2, if R1 is this, and lambda 1, lambda 2 is equal to, doesn't matter. No, sorry, it doesn't matter. Then U is just equal to the following thing. So here I have the same as here. Here I have so this one is the same as this. So here I have plus this one, and here I have this one. because this is an orthogonal matrix. Okay. So basically, if I meet for some representation, I meet Raka matrix of a size 2 by 2, I can immediately write it down using this eigenvalue conjecture. Another thing why is it useful is that if basically in general formula for this Raka matrix is unknown almost always, except for when I speak about SU2. So if I speak about SU2 or SL2, I know the general answer for this formula. It was I think Kirillov and Reshetikhin who got it, which explains how it looks like through hypergeometric function. But using eigenvalue conjecture for symmetric representations, I can show that any Raka matrix, any three-strand Raka matrix, is the same as some SL2 Raka matrix. So basically it works like this, that this Raka matrix, this 6G symbol, is equal to the same one where I add just one box for each row. Like this. And it's easy to see that if I take any symmetric representations by just subtracting the boxes, I can get to this one, which exists in SU2. So for symmetric representations, I can calculate basically all the polynomials just by knowing this general SL2 answer. And this, in a sense, shows why that initial story about why mutant knots are not distinguished by symmetric representations, because symmetric representations, in a sense, they're basically SU2 invariants, not SUN, but SU2. Okay. So this is this eigenvalue conjecture and how it works, and it is actually very useful. Okay, so
could you spell it? Raka?
Giulio Raka. And
Is it unique?
What do you mean?
It's uniquely determined by R.
It's determined by, so in other term for this is 6G symbol. It comes from quantum mechanics, where it is a story about SU2, where all these representations are just numbers, and so they depend on 6Gs. Yeah, so there's 1, 2, 3, 4, 5, and 6.
In general,
yeah. So
its very definition is it's uniquely defined.
Yeah, so it's defined for these 6 representations. Actually, not exactly uniquely, because there is, since it's change of basis, I can, it's defined up to a sign. So I can change the sign of this basis, and then it means that in this matrix, the sign of rows will change, or the sign of columns will change. But up to this, it's uniquely defined. Also, there is a question when the multiplicities appear, because then there's the question what these representations are. So if I have several of the same representation, yeah, then, so if I have multiplicity appearing in this, already in this stage, then the question is, what is this representation P I'm speaking about? And this is actually a difficult question, how to find them when the multiplicities appear. And actually, at the moment, it is not a fully solved problem. what should we do when the multiplicities appear. So we can say some things, but not everything. But basically, in this approach, when I look at the braid, in a sense, it doesn't matter because I can choose some basis in these multiplicities. And since for the braid I have just a trace, the change of basis doesn't matter. So there are some ambiguities in their definition, but they doesn't matter for the whole answer. And here, of course, I chose some signs, and I can choose them differently. So, for example, I can switch these two, or I can switch a sign of an arrow, and so on. Okay, let me skip the cabling procedure and speak about this story about two-bridge knots and abrasive knots. So basically, this construction works in the simplest way when I speak just about three-strand braids. It can be generalized to higher number of braids, but there appears more matrices. Higher number of strands, yeah. But there appears more Racah matrices and so on and so forth. But there is another case when the picture is almost as simple. And these are these two bridge of four-plate knots. So what can I erase? Erase this. So these are knots which are drawn like this. I take a four-strand braid, some crossings, but then instead of closing it like I did it there, I close it like this. This is called a four-plate representation of a knot. Basically, I can draw the same thing for a higher number of these plates, 6-plate and so on, but their situation is much more difficult. And these four-plate knots, they have two additional names. It's two bridge knots. This means that I can draw it on a plane just with two arches, two bridges. Yeah. So all the crossings can be put like this, that I just have only two bridges which come up from the plane. And another name is rational knots because they can be represented as a rational fraction, in a sense. I don't remember. Yeah, infinite fraction. No, maybe finite. Yeah, finite. Yeah. So what this representation of knot corresponds to when I look at this picture? Basically, it means that if I put a closure like this, that instead of taking a trace, I take a projection, and it's a projection on a trivial representation. So basically, for example, if I speak about SU2, it is very simple. I put, for example, defining representation here and here, and a square of defining representation is a symmetric one plus a trivial one. Yeah, representation of a size 1. And here I take just a projection of this trivial representation, because nothing, in a sense, nothing exists after this. And the same here. For SUN, the situation is a little bit more difficult because it means that if I have some representation y here, here I should have a conjugate representation, so that in their product there will exist a trivial representation. So this is a braid where I have where there travels two representations y and two representations y bar. But what simplifies it is that so basically, if I try to calculate it like here, like I did here, I had to take a sum over all representations q coming from the tensor product. But since I have a projection on trivial representations here and here, it actually means that instead of this sum, I have only trio representation. So instead of this, I have just Q equal to a trio representation. And again, I have the same thing, that there is a product of all our matrices which appear here. Just after that, I should take a matrix element which corresponds to a projection in this place. What this means is that actually there is only two Raka matrices and only two diagonal R matrices. So two diagonal matrices comes from the thing that there is a matrix, let me call it T, which corresponds to the crossing between Y and Y. So if I look here, yeah, so here the two strands would coincide in direction cross. And here, for example, the crossing is between two strands with opposite directions. So this will be one matrix, and this will be another matrix bar. And they are different because the reducible representations here and here are different. But actually, this matrix is the same as this one, and this one is the same as this one. And there are two Raka matrices corresponding to different placement of the strands in here. So one corresponds. Sorry. Okay. So one matrix corresponds to this placement of representations. Well, there is something here and something here. Another corresponds to this placement. And they are different ones. But basically, using these four matrices, I can again calculate everything. But I actually can go even further than that. Basically, if I look at this four-strand braid and leave it open at one side, this will be an operator which acts on irreducible representations in the product of these two strands and projects onto trio representation here. And actually, I can study even an operator like this. And this will be, so I have representation Y here, representation X here, operator like this. And using such elements, I can construct a much larger set of nodes than these two bridge nodes. So I can construct these so-called arborescent nodes. I can construct a tree from them. So I can put древовидные. So I can have vertices where several of these things connect. I can have some kind of branches which correspond to this operator, which connects different vertices, and so on and so forth. The only thing I cannot have is that I, for example, cannot connect them like this. I cannot have circles, because then this property is broken, and the situation becomes much harder. And so basically, using the same matrices, the same set of four matrices, I can calculate the answers for all arborescent nodes. But I can go even further than that, because if I look at this tree, yeah, and then leave it. Yeah, inside each rectangle there is any four-strand braid. So I just take any 4-strand braid and then connect them like this. And so in all vertices, I should sum over irreducible representation which runs in all the strands, and then connect them with these operators. But I can go even further than that, because this tree, what it does, it acts on irreducible representations in this pair of strands. And so in this sense, it looks a lot like a matrix. And so basically what I can do, I can take a 3-strand braid, you put it inside this 3-strand braid instead of a matrix. And get, I don't know, like a forest, yeah. So I have this 3-strand braids where I can put different trees in different places. And I can find the answers for any of these things. And actually, this aberrant knots is what allowed us to construct a polynomials of mutant knots. Because exactly, so the simplest example of this mutant knots.
You mean some example of mutant knots?
Not all mutant knots, but yeah, not all mutant knots. But there is actually a large set of mutant knots which are exactly aberrant. These are so-called pretzel knots, which looks like this. I have 2-strand braids, any number of them, which are connected like this. So this is some kind of generalization of torus knots when I can put them on the surface of high. So torus knots, I put a knot on the torus, and these ones I put on the surface of higher genus. And these are just 2-strands braids here. And basically, and I can have any number of these things here. So this is pretzel. And it's actually easy to see that they are aberrant because I can redraw them like this. So they are aberrant with just one vertex. And so they are parameterized by a set of numbers, so n1, n2, n3, and 4. And if I go through this mutation procedure and cut, for example, this block and rotate it, this will switch two numbers for me, n3 and 2. And so instead of not n1 and 2 and 3 and 4, I will get not n1 and 3 and 2 and 4. And this is some simple example of mutant knots. And actually from this picture, it's easy to see why symmetric representations do not distinguish them. Because basically, if representations are symmetric, then there is only one of each representations here. And this means that when I take this vertex and take a sum of product of these things, so it's sum of a product like this. So they are just, for symmetric representations, they are just numbers. And numbers commute. So independently on the order of numbers here, I will get the same answer. And for higher representations, some multiplicities appear, so they become matrices and they no longer commute.
And you managed to find examples where two mutant knots are distinguished by...
Yeah. So you need to look at representations to 1, like this. And they, well, not all of them are distinguished, but some of them are.
Yeah, and the simplest example is represented by which series of numbers and 1 and 2 and 3? If you don't remember.
Yeah, I don't remember. I think actually that there is maybe there is a problem with these knots. So some simplest examples are actually, so there is this famous pair of knots, yeah, Kinoshita Terasaka at Conway, and they are just to bridge knots. Even this is not needed. And they definitely differ by these representations. For the Pretzel mutants, at least at some point, they stop differing for this representation, and you need to look at this one. There is actually a paper by Morton where he says that there is some additional symmetry in mutant knots when they stop to be distinguished by this representation, and you need at least this one. And we actually managed to check this, but by different approach because this mutation is too hard. And actually, from the point of view of these representations, it is also understandable why it is so. If you look at this formula for eigenvalues, so there is this signs. And so if I take a square of these representations, the multiplicity appears. So there is something else, plus 2 times this one. And actually for this one, a matrix will have different eigenvalues. So one of them will have the sign plus, another will have a sign minus. So in a sense, it is not a true multiplicity. So they are still distinguished in a sense. And here, the first time when multiplicity 3 appears, and this stops working. So there is some insight in why it is so, but well. Okay. So do I have the time to speak about this virtual nodes?
Yeah.
Well, let me speak about one more thing here. So there is also a very powerful method coming through these matrices. It's called the evolution procedure, and it goes like this. So if I take some node, some series of nodes, which looks like this. So I have some set of crossings, and I call it E. And then, for example, just one crossing to the power of n. And it is somehow closed in some way. Then just knowing that the answer comes from our matrices, I can say that, well, let me look, for example, just at defining representation.
Yeah, what do you mean by the answer?
Huh?
What do you mean by the phrase the answer comes from?
I know that the answer is provided by a product of our matrices. Then I can say that the polynomial for the series should look like this. So for defining presentation like this. For higher presentations, there will be more terms in this sum. So without the knowledge of how what is here, how to calculate the whole polynomial, if I know some polynomials from the series, so in this case I know 2 polynomials for this, from this series, I can immediately write down the answer for the whole series.
Determinant coefficients method.
Yeah, so I can find these coefficients and find the general answer just by knowing that the answer is related to our matrices. Without, and this is basically what allowed us at some moment to find the answers for colored twist knots. Because just we know some terms of the series, some simple knots, and we can provide all of them. It's just a very powerful method, but not very general because I need to find this series. Okay, let me try to briefly speak about virtual nodes. Or maybe move it to a separate token.
May I ask
Yeah.
general
Yeah.
question? If you take all these invariants coming from all possible
They're the same.
U of n and from all possible irreducible representations, is it more powerful just Home-Fly?
It's definitely more powerful than just the Home-Fly because, well, for example, for these mutant nodes, yeah, just uncolored Home-Fly coincide. And colored Home-Fly can be different. So it's definitely more powerful than this one. It's a question if it is a full node invariant.
Definitely.
If I take the set of all colored Home-Fly polynomials, and why do you think so?
Real algebras are not enough to distinguish any.
Okay. Yeah, and there is a story by Vogel which allows, in this formalism, there exists this universal node polynomials, which are polynomials for any group, basically. But it's easy to write them in this case, but it's difficult to write them in this case. In this case, I should put a joint representation and then I can write it down. Maybe these are full node invariants.
And
but this
I
is
have
not.
another question.
Yeah.
There are some other sources from R matrices. Some other solutions of Young-Garster equations.
Yeah, there are, but well, there is the sum matrices which appears in integrable systems, but there is a problem of applying them to nodes, basically because there is no r to the power of -1. I have a relation that just r squared is equal to 1. Yeah. And this means that the node invariants become very simple. So are there any matrices which do not possess this property but are non-trivial? I actually don't know.
There are several sources for R matrices.
But why they are not applied to this study?
No.
To this specific study, because it addresses a different question.
Basically, if a matrix with spectral parameter is, well, it's applicable, but the answers will be very simple. They'll be uninteresting. And different matrices, well, the question is how to apply them. And actually, all these things, they're heavily based on the theory of representations of quantum groups. So this is what allows me to calculate Racah matrices and so on and so forth, and provide some basis on why this is valid. And it is a question what to do if I just have an R matrix, how to calculate all this. And also there is a question of, well, when I started from the Sierstein-derived formalism, there is a question of how to define this reversing metrics. Because here I have an answer which comes from these quantum groups, which were developed long before this story, yeah? And I basically know that if I can show that if I use this answer, the answer will be topologically invariant. But to understand what should I put instead of this when I have some general matrix, it's a different question. And actually, well, my student now studies a problem is that actually, well, as I've written, so Q from the point of view of physics is equal to this thing, and it's a root of unity. And for roots of unity, actually the theory of quantum groups is vastly different than what we're discussing. Basically, we're discussing the theory for large K, for very, very large K. And if you take a small root of unity, there appears some cyclic representations, semi-cyclic representations, and so their matrices look different. They have different eigenvalues, different number of blocks, and so on. And this is exactly the problem she had, how to find this reversing matrix. So there is some answers, but it's not easy to find them just looking at our matrix. It's a difficult question, especially for large matrices.
Sorry to prolong this virtual answer.
Yeah, maybe we can move it to...
Maybe about virtual knots, without giving definitions, will you explain very briefly what kind of results?
Basically, we defined conflict polynomials for them. Yeah, yeah. But maybe, okay, I can try to briefly present an answer, but...
The problem is that next couple of weeks we do have already plans for the seminar talks.
Well, I can try to present it briefly.
You explain the idea.
So, do I need to explain what virtual knot?
No need to explain what are virtual knots.
So basically, virtual knots were introduced by Kaufman, and so he suggested a method of calculating Jones polynomials for them, which is the following one. He defined virtual knots, and he defined Jones polynomial for them. Yeah. So basically, he said that if I have a crossing, I should replace it by these two things. And so instead of a knot, I will have a number of just circles, which are called ciphered cycles. So I resolve all the crossings like this. Then I calculate the number of cycles, and corresponding to the cycles is just quantum number 2. This is q squared minus q minus 2, or q minus 1. And this works for SU2 because, as we spoke before, reverse arrow means a conjugate representation. But in SU2, conjugate representation is the same as the initial one. In SUN, this is not true. So this cannot exist in SUN. So basically what I suggested was to replace it in a sense by a formal thing. By this one. And then instead of this dimension,
this resembles the fourth term in the previous.
This? No, this is virtual crossing.
Yeah, but it resembles the fourth term you had. Четвертый член, который вы добавляете в...
Not exactly, yeah, but there is some relation because the problem is basically the same. That if you try to use scalar relations, you are stuck. You cannot move to some simple knots. And again, for each resolution, you should define a dimension. Instead of 2, it will be n. The problem is that, well, it's easy to define a resolution here, but it's more difficult to say what is here. And it's easier to say what it is here for q equal to 1, then it's just a sum of these numbers n. But for q not equal to 1, you should show some rules how to define them. And basically, this goes like this, that through these things I can represent a knot through a fat graph. So let me consider some example. For example, this one. So it resolves like this, and here I have a difference between these two pictures. So for q equal to 1, this is n squared, this is n squared minus n. And when I move to quantum numbers, this should become, to give the answer, this should become n times n minus 1. But basically, I can say that this is a fat graph where each circle corresponds to a vertex in this graph, and this is a connection between two vertices. And there is also a direction on these vertices. And fat graph means that I should remember the order in which lines connect to the vertices. And then there is certain relations on these fat graphs, which allows to calculate dimensions corresponding to certain resolutions. So basically, for example, like this, if I have some vertex, this is vertex of fat graph, and there is just vertex with one connection connected to it, like this, then this is equal to n minus 1 times just this one, and so on. And so basically, these relations are one-to-one correspondence with the Rademacher moves. And basically, this is how one can define these conflict polynomials. There's also an interesting...
And you prove that it is well defined, yeah?
It's topologically invariant. It's because we just proved the Rademacher moves. It gives the same answer as other methods if you study just usual nodes. It gives something interesting for virtual nodes. What it gives for virtual nodes constrains for this one for SL2. Yeah, I think that it showed that it's independent of how you resolve this, you get the same answer. And it's actually also related to the story about Khovanov and Khovanov-Rozhansky, because, well, basically this is related to Khovanov. This is to Khovanov-Rozhansky, that these are the spaces, the dimensions of the spaces for which the homologies are calculated when you want to study that story.
What do you mean? You repeat all this V? What do you mean V?
Well, I and my co-authors, yeah, which are different in different papers.
Oh, okay.
Whether our distant participants have any questions, will you ask them?
Maybe they tried to ask something.
Ну, в чате все пусто, тихо.
Okay, you must have big tables of values of...
Well, I have a small table here, yeah, but there are some tables, yeah. There's actually, well, it's not very up to date and so on, but there is a site. So it needs redoing, so it's not in a very good form, but this site where basically the results of our scientific group are present. So this as well as many of the Straka matrices and polynomials and so on.
Also, you should have obtained some explicit answers for a certain series of nodes or links.
Yeah. So
not just for individual.
I'm trying to look. And this is actually one more interesting thing, that this evolution procedure, it even applies for these virtual nodes. So for virtual nodes, our matrices are not applicable. basically because it's hard to say what should correspond to this virtual crossing. So you basically would want for it to be equal to permutation operator, but then this whole structure of quantum groups stop working. So our matrices, you cannot calculate the answers through our matrices, but you can use evolution method still. Although you have no R matrices, it still works. So basically, yeah, we have some answers for series of usual nodes. There are some answers for series of virtual nodes. So just there's only some basic answers. Are there any more questions?
У меня вот такой вопрос есть.
Yeah.
Часто используют всякие диаграммы в виде ос для вот этих инвариантов. Ну, представляете?
Да.
А не получится какой-нибудь профит добиться, если использовать какие-то другие универсальные диаграммы?
Ну, во-первых, вот эта вот картинка, да, это другой тип, который, значит, многого позволяет добиться.
Это требует кос.
Ну, в смысле, это, потому что для кос мы знаем, как считать, да, поэтому, значит, добавляя это к косу, мы сильно расширяем то, что мы можем посчитать. На самом деле это можно обобщить и дальше, в смысле, что можно смотреть вместо кос, вместо этих деревьев, можно смотреть просто какие-то тенглы, которые будут также действовать. Но это вопрос, как для этих тенглов найти выражение. То есть для каких-то можно, например, вот...
В общем, дело в том, что матрицы приспособлены к косу.
Но нет, не только. В смысле, что вот такую штуку вот тоже можно посчитать, допустим. И это позволяет рассмотреть, это называется, по-моему, Whitehead double, когда я беру узел, да, и замыкаю вот такой штукой. И, значит, я могу посчитать двухнитевую косу вот из того, что я писал, да. Вот эту штуку тоже можно посчитать. Она известна, чему равна. Ну, не для всех, но, в общем, для каких представлений можно ее найти. И, соответственно, можно посчитать Whitehead double. Просто это применимо, но это дальше начинаются вот с методом эволюции тоже так же, как бы частные случаи, они не универсальные. В смысле, вот для конкретного случая мне надо смотреть, могу я это посчитать или нет. Искать способы это найти и так далее.
Диаграммы лизинга, которые как решетчик такие, или там
Книжки.
Да, книжные представления, конечно.
Но
нет,
они не приспособлены под R-матрицу.
Ну, в общем, надо как бы...
Здесь дешево не дается.
Здесь вот история стоит в том, что мне надо вот что-то найти, где я могу спроецироваться на непроводимые представления. Тогда все сильно упрощается. Потому что как только я могу спроецироваться, это означает, что сразу у меня ответы становятся... Ну, в смысле, что вот я сразу могу написать какие-то общие формулы для любой группы СУН, не надо какие-то такие детали углубляться, не надо